How are you?
I'm tired. How are you?
Same. I don't know how much time I will recount weeks before the end of the class. Maybe this is not yet the last lab. Maybe we will have one or two more to accomplish the projects. But the original idea that 55% of the projects will be done today.
Are we doing lab on that week or not? Because I can just tell you right now how many labs there are.
On the dead week,
It's the 11th.
all results should be in place. We will do like auxiliary lab just to prepare videos for presentations.
Okay, then we have
Okay. So,
after this one? After this
2 more after this one.
but still, let's like pretend that we do not have anything else and try to speed up now, because after Thanksgiving, people do not do things, right? I do. Due to generous sponsor, we have some snacks. And by looking around, you can find the sponsor. So you all do have an idea what to do. I will show it on a screen. And I believe most of you got some input from helpers, right? So I will do something primarily related to Morgan's project. So the whole class will do his project, so to say. Not completely, maybe first steps, but it is an important part of the class. It will take about first hour, and then I will just stop by individually. So you have got a couple of codes in the email, and you can either do your project if you want to like get through quicker. The last time I think I was distributing this little guides of steps, and they let me know if you need them electronically. Another option is just to follow, run these 4 codes. They are basically the same, only one parameter is changed there. Run 4 codes and observe what happens, and I will be providing instructions and explaining what it is. And the third way, just sit and relax. So before I will start project materials, I'll give a little forward for those who are listening, if you want to. It's not critically necessary. Maybe your own project is more important. This material and the first steps of Morgan's project will be covered maybe in the very last lecture of the class, so we are going a little ahead. If you do remember motivation slides for today's class, there was an important concept that there was a system that simultaneously experiences properties of nuclear and vibrational degrees of freedom, vibrational and rotational degrees of freedom. Same synergy of different degrees of freedom is a standard thing, because everything is multifold. And one of the most interesting, beneficial, useful, and practical synergy is between electronic and nuclear degrees of freedom. A little bit different from what was in the class. If you need examples, any organic dye which has grounded and excited electronic states, in each of these electronic states there are different internuclear potentials, right? So it's a synergistic operation of both electronic and nuclear degrees of freedom. Therefore, one needs at least 2 or maybe more potential energy surfaces and at least 2 or more electronic states. And there is a probability of transition between these electronic states and potential surfaces by different mechanisms. Can you do it? Yes, but it will be an intellectual challenge. It is not goal of the class that all of us become professional programmers, scientific programmers. We just need to get basic ideas, and these little codes are auxiliary. But before, we were always propagating only one nuclear degree of freedom, and we didn't have electronic degrees of freedom. One of lucky us, Steven, has a project with 2 electronic degrees of freedom for NMR doublet, which can be up and down. But it will be either his own secret project, or it will be exposed to the whole class maybe at the last lab if time allows. But what we are going to do today is outstanding in its beauty and complexity. We need to merge together electronic and nuclear degree of freedom. Okay, I think enough for forward. And yeah. Good, very good. Here is a little reminder of your choices, just if you didn't do your own records, and if you see something differs or someone is missing, it means that it was last-minute arrangement and you know about it. So let's be very practical and so probably it will be more reasonable if you just watch it working and then go over principles and details. Otherwise, it will be too boring. Did anyone try to run it? Yes, the one I will explain what's the difference, but the very recent, like in a few minutes before, are okay, so there are 2 potential energy surfaces, and this dash line, blue dash in the blue potential, originally looks very similar to what we had a couple of labs before. So it sits in the center and doesn't change its shape and position, minus some very little weakness. But with time, its height and area out under this probability distribution gets smaller and smaller, but because of conservation of probability, something appears with this red color in the red parabola, right? What is novel, different, and challenging in here? I will go over other slides, other panels as well. Before, we never practiced an analogy of schizophrenia. It was always normal for function. For one position in space, there was one point in the probability distribution for wave function squared. Now, for each position in space, we have two wave functions. How to interpret it? What do you think? Now we discuss it openly and collectively, and on the final presentation, Morgan will teach us what it is.
Sorry, what was the question?
There are two wave functions defined, like for each value of position, there are two values of wave function. It's same like plotting two orbitals overlapping with one atomistic model. And it is not set of eigenstates, it's actual what is going on with system. So the blue line is the part of wave functions that residing in blue parabola. The red one is the one that's residing in the red parabola. And they have it's like waves in two cups, and they have a wick. They can penetrate from one cup to another. But both of them are good quantum harmonic potentials, oscillators. Right? So for Morgan and his project, the goal will be just to assess which practical situation is modeled by these parabolas. How the initial conditions modify the outcome, what is observed. And we all will practice it a little bit. Before we go to this practical detail, I suggest we discuss a little bit what it is, what we already started, and then I will exhaust you with showing details how it is programmed. Just in case if we need to change something, we need to see the details. And I will give you heads up when I will start this stuff, and then you can just lean back and relax or do whatever your own projects are. Yes?
Do you know if this computer over here has MATLAB?
It should. If you don't, I can borrow your laptop, which I don't.
I crashed my MATLAB, so
You can take this one if you want.
I'm gonna check that.
Okay. So, do you have any protest or any questions about this paradigm of two waves in two different cups that look between each other?
Which one should we run?
You should run.
One minus.
You should run all. And this is very little exercise. For the project, you will need to generate like 20 of similar and run 20 or 100. It's nothing. You're not doing it with Abacus. Computer does it for you, right? So I will run others maybe as well, or explain what they are. And you may try and check what they are. But before, let's go through conceptual things. Please share any protest or irritation or misunderstanding with this figure, if you have some comments. Or you can support, like, oh yes, I was always thinking wave functions, but some, does it look natural or unnatural? Huh? So what is most unnatural? Well, if we add together these two lines, it will be overall distribution, and it will curve of the summation being integrated gives 1. So summation of these two is normalized. If we fill the leak, then each of them will be ideal harmonic oscillator. It will oscillate either in one or another. And you will see that there is a it's the same code, it's derivative of the same code. There will be parameters for Gaussian wave function like position and momentum. Right now it is set up to sit at the equilibrium position, and therefore it doesn't move, right? It's natural. The other one is has equilibrium position away, therefore it distributes and does some motion. Let me draw something. So this is not the whole story, it is oversimplified. Suppose we have diatomic molecule. And in ground state it has one average interatomic distance. If we excite it with light in the excited state electronically, if we promote electron to next orbital, the equilibrium distance may change and potential energy surface may change, right? So if you have a mechanism of jumping between electronic states, then the molecule will experience different interatomic forces, which means that for each of these electronic states, we will have, let's make this one shorter. For each of the electronic states, parabolas, and we use parabolas just to make our life simpler. Typically, it's something more complicated. Do have at least different equilibrium position. In addition to that, they may have different offsetting energies. So this is electronic offset. And if we know for sure that the system is in the electronic state number 1, then it will be wave packet only here. if we know that for sure electronic state is in another potential, it will be wave packet somewhere there. Right? But what if it is halfway here, halfway there? So psi 2, psi 1 of x. But how do we mathematically record data if we want to describe the situation? So we are not yet approaching the way of solving it. We just figuring out the basis. One way, and I'll tell you right away, do not listen to it, it will be wrong. One way would be to say that wave function is product of psi 1 of x1 and psi 2 of x2. And then it will be like product of them, because these two dimensions are kind of different. No time for arguing it. It was only hypothetical to show possibilities. They are of the same nature, and remember when we were doing 2- and 3-dimensional boxes, we were doing multiplication of wave functions, but we were multiplying wave functions to dramatically different degrees of freedom, like x and y. Here it is still the x. What is our second degree of freedom? I suggest we do it in form of informal discussion, because it's all the things can be derived rigorously, but then it will take 3 semesters. And I believe in your scientific intuition. So what is changing when we get from one state to another state? Energy, and we started talking about synergy of different degrees of freedom. One degree of freedom is nuclear motion. What is another degree of freedom? If you are thinking whether to sleep or to wake up, right now is a good time to wake up and think actively. There will be an important conception, and it will be like throwing minds off. There is another degree of freedom. What is the second degree of freedom? What is changing if you go from one to another parabola? Yeah, absolutely perfect. You are ready for this problem. And like we are going from LUMO to LUMO plus 1. We are jumping between orbitals. So count of orbitals, count of electronic state is our different degree of freedom. Why it is throwing minds off, why it is not usual, one is a new concept. Because we got used to think of degree of freedom of something continuous. A little bit of effort was in transferring operators from continuous to discrete matrices, but still we were considering that sometimes we can go into continuous. But here it is dramatically discrete. So degree of freedom number 1 is x, degree of freedom number 2 is electronic state. Or we can say it is number of electronic state. So it will be just either 1 or 2, or we can count them 0 or 1. And I was reserving the next words for much later lecture material, but I will disclose the secret now. This was the reason why we adopted Dirac notation, to be able to play with degrees of freedom which are discrete. So here x can be equal like 0, 0.01, 0.02, continuously, right? Take all values. Here for these discrete electronic states, it can, in our approach, it can have only two values, 1 or 2. And if you want to call them, you can say electronic wave function is equal 1, or electronic function equals 2, where 1 and 2 are electronic states. One more step. What if the system is in between, in like halfway excited? If we have part of the probability is that it is, I think Morgan was telling about Schrödinger cat in the first axioms. So what if 1 and 2 is life and death of Schrödinger cat, and it is halfway with probability 1/2 alive with probability half dead? How do we write a wave function for it? I know the answer, but if you can, we can add them together. So psi electronic equals 1 plus 2, and we do have expansion coefficients c sub 1, c sub 2. Make sense? And now these expansion coefficients, c1 absolute value squared plus c2 absolute value squared, should be equal 1 if it is a good normalized wave function. Good? Feel free to protest or to stop me.
So,
If
what good does it know, or what good does it do knowing when they're in between, how to represent that? Kind of a complicated question, but
once again,
what, how does it help us to know how to represent when it's in between the states?
okay. Suppose you are inducing transitions between the states by quantum of light, right? One way of thinking about it is that infinitesimal short, infinitesimal small particle of light hits system and immediately converts it from one state to another. But another, so it is very quantum discrete way. But if we come back to a classical picture, light is oscillations of electromagnetic field. And if our quantum has amplitude of these oscillations very small, so it's just system being excited by appropriate frequency but small amplitude, then this transition from ground to excited or whatever, excited 1, excited 2, will be not instantaneous, but it will be continuous. Result in measurement in the Schrödinger cat will be always either 1 or 2. But quantum state can be in between, 50-50. And we need a language to describe it. Make sense? Good. If you were not protesting and if you were supporting this idea, you are done with physical chemistry and quantum theory. Absolutely. There will be no new ideas anymore. This was maybe main idea of the course. I'll keep entertaining you and offering you something to do, but you are already over the top of the mountain. Now, from now on, we are going downhill. We need to merge degree of freedom number 1, x, and degree of freedom number 2, which is this discrete one. You see it? With your permission, I'm going to erase. Okay? There is no promise that recording will be sufficient, but successful. But about 90% of times it's good. It's watchable. So I'll erase this stuff and combine something out of here. So when we have a synergy between different degrees of freedom, we need to multiply them. Okay? So our big wave function, which will be depending on electronic and nuclear degrees of freedom, will be product of the smaller wave function, which depends on x for nuclear, times C1 1 plus C2 2 for this one for nuclear, this one for electronic degrees of freedom. Good? Do not hesitate to stop and protest. Lack of protest means you completely support and agree with it. So we are coming closer, right? We are not yet there, but we will be there very soon. Right now, it looks like the wave function is the same for both electronic states. But the most adequate way would be, instead of factorizing nuclear function outside, it will be correct to think that expansion coefficients in front of these states 1 and 2 are wave functions in a nuclear sense, which means these 2 degrees of freedom are not just multiplied, they are entangled. And if you use the word entangled, I don't know how you even if you want, you may talk directly to whomever you are helping. I'm just entertaining everyone. It shouldn't deviate the projects. So if you use the word entangled in any of your scientific activity products, it will multiply attention to your work times 10. So instead of this notation, we should write that this big wave function is psi nuclear of x1 times electronic state 1 plus nuclear wave function 2 for electronic state 2. So if of x, if we accept the concepts behind this notation, then there will be nothing new in the rest of the course. It will be just continuation. And the dynamics that you see here is implementation of this concept. So this blue and red are states 1 and 2. And in each of the states, there are wave functions, nuclear wave functions. But they're not independent. They are connected. If we require this big wave function to be normalized, and we know that Brian cat of this and Brian cat of this will give 1, it gives the requirement that psi nuclear 1 psi nuclear 1 of x So absolute value square of first, absolute value square of second, integrated over all space, should give normalization 1. Therefore, it is like 2 cups with a liquid between them, or 2 containers with liquid. passing through. Okay? Any suggestions or questions? Why do we need it, and what is outcome? What is criterion of success in this little problem? What is the main observable? What should we look at? Huh? Yes. Wave functions are beautiful. I love them. Especially orbitals in atomistic calculations. But they contain too much information. Wave functions typically do not exit from interferometer or any instrument. So we need, even if we do just a little thoughtful experiment without instrument in our thoughts, we need to identify something simpler than just wave function. Suppose we have two, and we do, there will be absolutely no time to go over all details, but suppose we do have two to propagate this complicated wave function in time, which means we will put variable t here and there, here, 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 and there. Will it affect normalization? No. If you are answering no, it means you are doing perfect in the class, and if one would make an exam with multiple choice, you will pass for sure. Your signs that you answered no is very good. It's healing to my heart. But the relative proportion, if you do this integral over x and integral over x there, do not need to be constant. So we can call it probability that system stays in state 1 as function of t, probability that system stays in state 2 as function of t. Their summation will be always 1. But the relative proportion is like 1% plus 99%, or 50 and 50, or 20 and 80. Okay? Very good. Thank you for the support. So, and we will go very soon through the code where these proportions are introduced. Here they are. If you feel free to chat, it's more important.
Oh no.
Keep going, it's fine.
Well, just to clarify, so essentially by adding time dependence, or the time factor, to our normalized equation, we're just going to solve for the probability of finding an electron in two different states.
Mm-hmm.
Okay.
Yep.
So if you didn't add that time,
It will be super boring.
okay.
So when you were running the code, did you saw this image? So please try to run. Doesn't matter. I did run. Let me check which one I did.
The plus one gives you that, and then some of the other ones just gives you like something across the top. Yeah, the one.
Yeah, I did 1+, yes. But you notice this, it is not labeled, but we can do it easily. So this stuff shows how the probability changes from, so it's probability in state 1, probability in state 2. They both are within, between 0 and 1. Their summation will be always 1. but it is an information at which quantum state our system is. Okay? So basically it is this P1, P2. Question to Alyssa. Oh, okay. So we would be a good candidate just to draw this probability as function of time as a main result. Yes, it oscillates, but it is still too much information, too many data points to follow this trajectory. Look, here it is mostly as a straight line. What do we do with straight lines? I know, typically we do not do anything with stuff in class, we forget about it and go to relax and I don't know, each one has different hobbies, but if you need to describe a straight line, what do you do with it? Huh?
Let's just like find the slope.
Yes! Did you hear it? You're a perfect accomplished scientist. So if a scientist does see a straight line, he or she finds a slope. So if you identify that this probability changes linearly, you can just find a slope. What will be the slope of this P1 of t? I'm not asking for the answer. I'm asking what is the slope in the like. Huh? Correct, but it is a practical answer. More abstract. If you have function, how do we extract slope from it? Huh? Yes, you are confirming your reputation. So if you do dp1 over dt, it will give the slope. The slope is just one number. So we reduce very complicated problem to just one number. And the main result of each run will be this slope. So if we forget about like details, modeling of realistic systems, and just think practically, if I am get paid to solve this problem for hire, what is my final product? I run it with different conditions, and I record slope. Just one number. And then I can put correlations. Which parameter did I choose? Did I change? Like, let me bring it. I can change initial equilibrium position. I can change energy offset. I can change initial momentum. And then I will run it again and again several times. And for each value of parameter, I will record the slope. And let me assure you that there will be strong scientific value in this. It is already with models at this level of complexity, with this paradigm, it is a competitive research. You do not need more. You just need to explain how these parameters are related to a realistic problem. We do not have time to explain the parameters. We will learn it from Morgan when it will be his time to present. Good, but we do have time to play a little bit with these codes, with this specific code. So let me I do not want to erase it because it's really important. I'm going to set up a little educational task that I invite everyone to do it, and it will be mimicking the research project of Morgan. So his actual work will be a little bit different, but very close. So I suggest to take as a parameter the energy offset between these two parabolas. Basically, in these four versions of codes, there is only one variable that tells are they higher or lower than each other. And as a main outcome, we will find the slope. Tp1 over dt. And here you put energy offset. To warm up your interest, I will say that Dr. Rudy Marcus got Nobel Prize for solving this problem without computer for a couple of specific examples. So it's on the top edge of chemical research. So energy offset, and here the version of code. Version of code is a little bit silly because I did a silly thing. I changed one parameter and renamed the code. One can just, it's like line number 9, like D, E, off, something like this. So we have 1 minus, 0, 1 plus, and 2 plus. So let's write down here what are the values of energy offset, and find and run the code 4 times, or 4 versions of the code, and write what are the values of the rate, and then just discuss it. I suggest to go this way because time is limited, and if we go rigorously through all steps, it will be a killer. And if you do this little exercise, it will bring inspiration and understanding of concepts quicker than anything else. Okay. Yep. I intend to finish this stuff in about 10 minutes, and then I will be visiting one-to-one. Okay, so let's do a slope of this line. It gets to 0.5 within 5,000 steps, right? So it's like 5 divided by 5,000. It will be 1 over 1,000. Which version was it? 1 plus. And what is the value of offset? Here, DE off, line number 7.
1 over 10,000, correct?
Correct, yes. So we are looking on 1 plus. The value is 0.0074. 0.0074. We are here in atomic units, and the slope is 1 over 10,000. Okay, now there is either downvoting another version of code, or I will just replace number 1 by number 2. And just to avoid confusion with previous notations, call it 2 plus. Now I'm going to erase. If it would be my project, I would do screenshots and put them in PowerPoint, or later when repeating. But now, just to avoid excessive windows, I will close all of them. Okay. And I'm running 2 plus. So what do you see as an observation? The blue is twice higher than before. It will be an intrigue until it runs into the end, but do you think it transfers from blue to red quicker or slower? Just by observing. Slower. Basically, the energy offset, if there is no energy offset, it is resonance and it is expected to transfer quicker. We increase energy offset and it is slower. This blue stuff almost stays where we prepared it, and the red one performs some motion. Okay. Let's find our favorite figure. Okay, this, as we discussed, it is slower, right? Noticeably slower, right? And maybe it is not always the straight line, but we can approximate. Think of it as a straight line. And what we can do to erase these upper lines so they do not affect us, and then look, so it is only the one that starts from 0. So what we can restrict our interest only to the initial fragment of line, because otherwise later on it starts mess. So we can probably go up to the 2000. So it's it reaches 3.5% by 2000, or maybe approximately 4% by 2000.
If you click on that point with the mouse, just like click right on the curves. If you're not selected.
There are several, like I need to maybe disable this. Yes. I am not strong in math. Can you help me dividing these two numbers? Huh? So like approximately 4 by 100 divided by 2000, right?
Yeah, 4 zeros and then a 1.
Okay, 4 zeros, 1?
And then a 1.
No, it cannot be 1 because there is 4 and 2.
Oh, I did those numbers. I did 0.03 divided by 20. 2080.
So what do you get? We can do it on MATLAB.
Where's this little closer?
So 2. 4 zeros and 2. Okay? And here it was 4 zeros and 1. 4 zeros and 1. No?
Yeah, wasn't it like 5?
Yeah, three zeros and 1. Okay. So it's about 5 times. So we got it about 5 times slower, right? Please, you want to correct it or?
Shouldn't it be for the 1 plus? Shouldn't it still be 4 zeros? Because it was 0.5 over 5,000.
It's 0.5 divided by 5,000. 3 zeros and then a 1. Done.
It's 1 times 10 1 times 10 to minus 4, and here is 2 times 10 minus 5.
Yeah.
Okay?
Yeah, because 1 over 10,000 is that number.
Okay, so here we get 5 times slower, right? And the value here was this much multiplied by 2. So 0, 148. Okay? Now let's check what will happen if you have 0. Will it
There's a code in the command window, doesn't it? It spits out the rate,
It says like an A array.
but it doesn't match.
yes.
That's the overall rate?
It's for educational purposes, I suggest we do it manually.
Okay.
When you will come into production queue, of course you will not do it measuring slope on the screen. So I just replace 2 with 0 and save as 0. Save. I'm going to close all windows, even if they have beautiful figures, just for to avoid confusion. So you see, now they are in resonance. Hypothetically, from our intuition, it should be the quickest. But we do not know before we try. Maybe it will be the quickest in this time, but it's not always this way. Now you see it drops in the blue potential and grows in the red potential. So the shape of wave functions display minimal oscillations. It's just multiplying by a factor. In this equation, it will be just Gaussian here, Gaussian there, without much change, just multiplying by a constant. And okay, it looks like about the same as here, or maybe a little bit quicker. Let's find the slope. Uh, 0.6 divided by 5,000. .2. So it will be 1.2 10 minus 4. So it looks like a little bit quicker, right? And now we need to try the negative. This is the image that we can show if there is no time to show movie, right? It starts in one and then appears in another one. And this one is the rate as a derivative of the product over probability over time. So it oscillates, but there is a mean line, like I think here it's 1.3 to 10 minus 4 is what we did manually. So this average line. Okay, erasing it. Now putting -1. Save as. Minus. Now our product is lower than reactant, right? What do you expect, quicker or slower? You're right. You're ready for your project. You have an intuitive vision of how it works. So there are two factors. One, that it is again off resonance, and there is upwards in energy, which is always not a good idea, right? So it's like endothermic instead of exothermic. So we may hope that some little one appears in the red, but it is so much slower that it is hard to see by human eye. So here the result is not obeying our linear slope, because if we do it at a very few steps, it may show like much quicker. But if you approximate first steps as a line, but if you take any point there, it will be slower and slower and slower. So one can probably put the error bar, or we may come to an idea that the strategic planning of research had one flaw. The rate is not the whole story. There should be at least two characteristics. In addition to the rate, if it grows linearly, it can go to, like here it grows infinitely, but it may come to a saturation, to the value of probability at time equals infinity. And we can call it yield of reaction. And probably one needs to record both rate, which here will be bigger than anything else. It will be, I have fear to record it. But in addition, one probably needs to add another column, and in addition to slope, rate, to set up yield, which will be value of product probability at time equals infinity. Any questions about this thing? To have most of the project unified, the suggestion for Morgan is to use +1 only, but to modify initial momentum. And I would be very happy to go over the code, how it works, but then we will suffer for other projects. Maybe I'll share the records from last year, or do a little bit on the methods, how it works when we meet next time after Thanksgiving. Okay, I'll go over the very minimal parts of the code without details, only to be able to operate. So, Morgan, you need to talk to your graduate student helper to get idea of what parameters are, like curvature. The mass here is a couple of thousand times bigger than mass of electron, and you may find out what it is, why it is this way. But if we go through, you will see that there is a p-naught variable, and p squared over 2m is kinetic energy, and kinetic energy is the same as temperature in some sense. So one can set up larger value of p-naught, and see how it will change the overall run. Do you have any expectations from what is being changed if one adds momentum to nuclear wave function? Will it be quicker or slower? It's my expectations as well. So you see it, initial momentum immediately promotes it up, right? And then it doesn't matter for this wave packet where we are. So it has higher energy, and it vividly helps tunneling, not tunneling, just promoting probability from blue to the red, right? So with naked eye, we see that heating will solve all problems. And the idea, practical idea, if you do not get into deep theories, is to make a table like this, where argument will be momentum or temperature. And this is common motif for everyone, well, for about half of the class, except Stephen and partial. Well, Amelia and John will play with momentum. And I think it is enough about Morgan's project. Let me just quickly show another interesting thing, that here it grows, but it grows not constantly with constant slope, but with steps, right? Not continuously, but with steps. So it corresponds to wave packet passing through special points on this profile. Okay. Any questions about this thing? I would really love to go over it. Just it will kill the rest of the course because of lack of time. So let me bring up the list. And let's just chat one-to-one. Morgan, you're happy? Explanation of parameters. You can start running, changing momentum and recording rates and yields immediately. So, in some sense, Morgan got preferences. You with guarantee can complete your project today in the remaining hour.
So then should I continue to do like manual slopes, or should I use that value that it's putting out?
Create a table, put manual slopes, but then learn how they correspond to what is shown in the code. And you may record these equations because it is what you'll explain to when you're presenting your thing. Oh.
Which code?
Neither one. I need to send you a special code.
Okay.
Maybe I will do it as a first priority right now. I will just pull it out and send to you.
That would be wonderful.
Okay. same thing based on the detail flow. I think it's very possible.
So the black line represents the pulse. The sort of orange and red line, blue line represent the electrons going moving through various positions on the blocks here. But what did the yellow and purple one represent?
I will stop it by just saying was but we need to have that whole overview of
I have it.
You've got mail. You've got mail. About 40 codes. More than 10.
I only got 31.
Ah.
Why so many?
You know my bad habit of renaming code after changing one variable.
Okay.
So just try running them one by one, see what observations, and I will make a circle, come back to you and see what happens.
So I ran this one with just the normal parameters.
Mm-hmm.
So do you want me? Okay, so you said to use like the +1 to do these, right? But then change just the different parameters.
P0.
Change just P0. Okay.
Yes, and do it in Excel table because you may want to change it like from 0 to 100.
Okay.
And you do not need to like do it like 0, 1, 2, 3. You can do like 0, 1, 4, 16, 25, and then see if you can do a rough scanning, and then if you see the trend, it will be enough. If not, then do with more finer grid.
Okay, so I should just change the P0 values and record the slope.
Yeah. And try to open Excel and record it right there.
Oh, right.
Send me an email saying to look at line 32, line 60, and line 66 as being points of interest.
Okay, let's just open the
So,
code.
see if I can make this window bigger.
Can you do it a little smaller so that I can go into command line? About it's good enough. Okay, look through. Number of ensemble. There will be ensemble, number of ensemble. Where is the end of this cycle? Then there is another overtime steps. So it looks like we are putting variables all row, first, fourth, second, and third. sorry.
Oh, it's fine, Doctor. It's fine.
Did you run it?
Yes.
Right. Okay. Yeah, I need a few seconds more to. Very good. Huh. Wait, can you teach me how to get to the code?
Oh, you need to click on editor.
Okay, thank you. ASX, okay. C. What's going on?
I can't remember. Maybe later you can try it to see if there's any difference.
Let me see. Where did it stop? Oh, no. You're running another code, right?
Yes, I was running another.
No, then you're not clear all variables, and now P underscore echo. Save. So it for each element of ensemble, it slightly changes energy. Basically, what we were doing there. Right? Here we were changing it drastically. Here it changes just by very little offset, and the offset of offset of energy. So this is one that you recognize, right? And this one is no. We need not this one, but there should be. The way to rotate this thing.
Wouldn't it be?
Oh, or maybe it's still running.
You're probably still running. Is it supposed to do that?
Therefore, it was stopped there. So, well, can you look at the code while it is running?
Because I've had this computer for a while, I can tell you from the sound of the fan and the way the mouse is moving, we're using all of the computing power.
Yeah, well, if it's not sufficient power, just run it on this desktop. It's not a excuse me, optimal way. You better spend time on discussing rather than watching how it goes. Let's just stop it. So yeah, let's stop it here. Practical. One of the important practical thing is to recognize the meaning of these three equations. If you do have like scratch, and it will answer the question that you were posing to me. Let's bring more chairs and comfortably. So, in your just click it. When you were asking a question, you had this globe, right?
Mm-hmm.
This X, this Y, this Z. And then acting by external pulse onto doublet corresponds to change of the specific trajectory on the surface of this globe. Letting it to move without when it is either in ground and excited, it will be north or south pole. When it moves like according to free induction decay or just free motion, it moves here. So we need three numbers as x, as y, as z, as each of them as function of time. Good. So you do have the rho statistically averaged. So it's like start rho and then 1 comma. Instead of writing stat, I just put bar on top. 2 row 2 1 bar t t. So as soon as you know this four numbers, so-called elements of density matrix, and just there is no time to go over all rigorous things, but we had it in class, right? And I remember both homeworks I'll send them to you, but right now this is of so much higher priority. So suppose we know this, and based on these four numbers we can get these three numbers. Meaning of these three numbers looks like you already went through Wikipedia or other sources and you got what this.
Yes, it has the. These would be the four numbers you're talking about. The row.
No.
No.
But
Density alpha.
super. I like dealing with you. It's four numbers here. Just instead of 1 and 2, one can use 0 and 1.
Okay.
Only two numbers. So if one, the meaning of this row 1, 1, row 2, 2, row 1, 2, row 2, 1, this is occupation of state 1, this is occupation of state 2, and those two are coherences. Coherences between 1 and 2, coherences between 2 and 1. The meaning of this row ij is just psi I psi j. So if you know wave functions in the discrete basis as we discussed there, so it's all connected to your thing. Then you have this row. So S,
Yeah. Okay.
what is SZ according to your reading? Do not read right now. Tell me what you think or what you remember. How it is called.
Does it relate to the formulas you've been using on the road?
It is related, but not directly. So rho sub z, and if you want to make correspondence to your Wikipedia article, this is W,
Oh, let's have it.
and its name is inversion. Inversion of population. So it changes from -1/2 to +1/2. So if we take row 2, 2 minus row 1, 1, divided by 2. So if all population is in state 2, it will be 1 minus 0 divided by 2. Then it will be 1/2.
So basically, our goal is to find out the ideal condition
If
for
this one is 0 and this one is 1, what's the result? -1/2.
which kind of parameter can I quantify?
Row 2, 2 equals 0, row 1, 1 equals 1. So it is changes from -1/2 to +1/2, and it's like if everything is in the excited, it's 1/2, if in ground, minus. So it's like inversion, difference between populations. So it is S sub Z or W in this notation.
Okay.
So if you care only about excitations, ground or excited, we need only SZ. But if it is coherent experiment with pulses, one also needs magnetization in X and Y. So they are composed only of those. And they are called, this X is called, in this notation is called U, and this sub Y is V. Okay? So if you add together off-diagonal elements, row 1, 2 plus row 2, 1, and typical one divides by 2, it will be SX.
Something wrong.
If it will be row 1, 2 minus row 2, 1 divided by 2i, it will be SY. So those elements can be imaginary, but if you do these things, then you will get compensated. So I'm not sure if I'm giving immediate logic, but the wave function, if known, allows to find density matrix, which we can rewrite either in this list or better matrix is written as a matrix. And if you know the density matrix, you can find this projection of spin, pseudo spin, which gives magnetization, which is observable, which changes over time. So let's look over the
one question.
Please. Yeah.
Well, I think I have the syllabus in the front of this. So, I actually bought all of the recommended texts.
Mm-hmm.
So, is there any section in those that you would recommend for reading about this?
Yes.
Which book and which section?
This book is superior to all of them. It has everything. I will. If you're not super busy after the class, we can walk to the office and quickly navigate you to the right page, or I can send you an email later. But if it's safer just to go and look at the book together.
All right.
So
I'm not busy.
Yep. It's the first book out of this four is adequate for third year undergraduate and even simpler. So every of us in the class can read it within like 5 hours or whatever by spending 5 minutes after each lecture or before each lecture. But it is like a little childish. The last one has everything, but it is designed for upper scale graduate class, so do not expect yourself to find time to read everything. It's more like looking back into the content for keyword content, and then you find spin, block, sphere, and then it will get you to the right page.
Okay.
And it looks a little heavy in notations, but it's written without any intellectual jumps. If you slowly read it, one understands everything. So it's just a little long, but the best book on quantum theory. So you are browsing on the surface of block sphere. If you apply light, you are going this direction. If you let it free evolving, you go this direction. The code here, the blue line is row 1-1. The red line is row 2-2. Purple and orange are 1-2 and 2-1, or whatever real part. Why there are multiple lines? Briefly, because of the ensemble. We are going a little bit away well, basically, if you know how to propagate wave function, you can propagate density matrix. But there is in this code there is a way of direct propagation of the density matrix with so-called Liouville operator. Put here row 1-1 at time 0, row 2-2 at time 0, and so forth. So let's navigate to this place in the we set up Liouville operator, and each time step the propagation, our motion forward in time from past to the future by time interval d tau is by exponential matrix of going from this four numbers of row old to 4 numbers of row new with this Liouville operator. So it's same as
So this is the parent
dt
operator.
is same as evolution operator, but for density matrix. But if you look into here, there will be offset. Offset is how far the frequency of your
Just
pulse
massive not. Oh, okay.
is differs from E2 minus E1. So
It's a good sign. Alright.
if this frequency
Why did it go back?
and
Back to the
energy and transition are in absolute resonance, then it will be 0. But if we have an ensemble of many samples, this offset will be randomly distributed. Some of these frequencies will be a little bigger, some of them a little smaller. Why? If you have different molecules with same stoichiometry, absolutely same like nucleus, but they are just in different position, in different space. They experience slightly different environment because other molecules around come in different configurations. Maybe higher temperature, maybe different electrostatic angle, and all these factors together bring a little. There is a word. Disorder. Disorder ensemble. So we take 40. 40 is just because either myself or computer is lazy and you don't want to overspend time. 40 is equal infinity on this scale. So we take 40 values of offset, a little bit of negative, a little bit of positive, and run this evolution for density matrix for each of them, and then add together. Like if you have ensemble equals 1. Rho 1 from ensemble equals 2. Ensemble equals n capital number. Divide by n capital, then it will be statistically average value of Rho 1. So especially if you will deal with off-diagonal elements, this offset makes the propagation along equatorial line quicker or slower, or maybe in the opposite direction. And if we create system in this superposition, then part of them will go quicker, part slower, part maybe in the opposite direction. And if we let them go and then add together, you can consider it as like vector 1, vector 2 going from center to here. And if these vectors will be equally distributed on the equatorial, then arithmetic expectation value will bring us to the center, which means no magnetization. So originally, in an ensemble, you create a system with strong magnetization. All spins all magnetization is oriented in the same way, and they interfere constructively. But due to ensemble properties, they start with free evolution, and they come into different directions, and then after vector summation, there will be destructive interference, and overall magnetization is 0. And this is called free induction decay. If we look onto this line, it is projection is like sx squared plus sy squared, which means length of the block vector as function of time. If magnetization is big, this one is big. If it comes to 0, it disappears. So originally it is large, and it is this one is contribution from this polar thing, but then polar thing
So basically, like the higher temperature.
is dash line gives this sx plus sy. As soon as they come to destructive interference, it disappears, which means spontaneous disappearance of magnetization. And if you just describe this one, run and give illustration, it will be sufficient. If you have curiosity, second pulse may make them to run in the opposite direction, and after some time they come into the constructive interference, and it will be spin echo, photon echo. And interesting, the time here and there is the same. Enough?
I think so.
Let's talk briefly.
Okay.
challenging.
Yeah. I mean, hey, in the spring I'm planning to do research.
What was that?
In the spring I'm planning to do research on some frustrated Lewis pairs.
Oh, that's
You-
pretty.
using-
Doctor.
No, at MSU.
Oh, got
Different
it.
professor, not here. So
Oh,
this will be helpful, I imagine.
yeah, for sure. Maybe it's related fields. For sure, it's going to be a really good one for you. Yeah.
I would just do it all include this part
Okay, do a PowerPoint instead.
Yeah, regular. Yeah, because arranging a huge amount of data, start saving images, label them.
So you basically just modify the scale.
You're trying to develop some strategy and for
Okay.
Interesting.
What
Yep.
works it should say any move.
Oh,
And you can immediately run the cell label it properly and upload it.
okay.
Then you can insert
So do you know the deadline of turning into the final slides or something like that?
No. I imagine it's going to be after Thanksgiving.
Like this mid-December.
Like early December.
What is that?
I imagine early December.
Early December.
Since this is like going to take the place of like a final test, right?
I don't know.
Since like we haven't had any exams.
Honestly, I have no idea.
So you want me to share? Or and then
I can talk to Dr.
is there
Keller.
anything with like
Yeah.
the presence of American
Yeah,
Or
yeah.
do you just want me to look at last year?
Yep. Thank you.
But I heard you say wow when I mentioned that I bought all of the recommended texts. Right?
What was that?
I heard when I mentioned to Dr. Killen that I bought the recommended texts, I heard you say wow.
Yeah. Nobody does that.
Well,
This is gonna be like more than $500, right?
I think it was 700 total.
Fuck. Are you gonna resell it or are you gonna keep it?
I'm gonna keep.
What?
Well,
Are you gonna go to grad school or?
I would like to.
Did you apply?
I went to the grad school meeting that they had here, and I'm going to be speaking with a person who's giving a speech about their research at grad school at my university on this Friday. So that's two that I've investigated so far.
So, NDSU and MSU?
Well, MSU doesn't have a chemistry program,
Oh.
but it's some sort of relationship between wherever they are in MSU.
Sure.
So yeah.
Sounds great.
Uh,
Oh, hi. You poured a lot of money in there. You must be rich.
No, but my brother is.
Yeah.
He is an electrical engineer.
Yeah.
He works for DigiKey Electronics.
Yeah.
It's like the
Fancy.
world's 5th largest electronics parts supplier.
In Fargo.
They're not in Fargo, they're actually in Thief River Falls, about an hour away. So yeah, it's like, hey, I have books for my classes. Okay, how many? Here you go.
Fuck, really?
Yeah. Like I tried to tell him like
Because your brother graduated from
he graduated from NDSU.
Damn.
So
Wow, man.
got a good brother.
Yeah.
Jealous.
I have got a 5. Well, let's see.
Everything else is paid for.
I've got a box about this big filled with textbooks, and a shelf about this big filled with textbooks, and books just piled around my room at my parents' house. It's just like,
Should go to the restaurant.
yeah.
I stuck it in the question, like basically gave us what the
Can I have to?
You can. They're
Yeah.
like when he was like so like you took notes on what he said, right? What he said specifically was like one question in each chapter that is like exactly what he was saying. So I'm not saying I'm not saying that that's exactly what it's gonna be, but he was reading from a text. So you know, when he was telling us on it, he was looking right at the text. So you guys yes. So at least when I took it,
Each one which is generally corresponds to rotation form.
because I'm pretty sure like he's not gonna make evidence off like the actual textbook.
Oh, like the example
Yeah.
problem.
Oh no, it's like whatever it is.
His slides are exactly the same. So it's like
Yeah. I'll figure it.
I'm not really that worried about it. It seems pretty easy, and then like, okay, yeah. Last question, question 9. I'm pretty sure. I think it's exactly the question. I think it's homework problem 24 in chapter 15. I'm like pretty sure. Like, yeah, for the last one, because like Sheree and I were looking at it, and it was like pretty accurate.
You have some food for thought, right? You have food for thought.
Yeah.
That was last.
Who's next?
I have to go. I can ask some questions. So email? Okay.
But we need to meet about project before Thanksgiving break.
Okay, that's not
So
problem.
that we will have a chance to enjoy 6 days for the weekend. Not only with fun, but also with
Are you free on Monday? Is that enough? I think it'll be enough, but I don't know.
Yes, I will stop by everyone by this time. It's a little longer.
I just have one question.
You don't, sorry, you don't need to do the meeting. No? You two do not need. Kristen and John. I will talk to you if you're not doing it. Morgan, but like, it was your day today.
Yeah.
I just have one like
Yes.
hypothetical question. Well, it's not hypothetical. So I have a reaction that I like that I would like to follow, and I've been looking into it. And I know the reaction rate, but there's not much on the activation end of it. So could I do instead of like, could I like backwards calculate the activation energy? Is that possible? Okay.
But the forward calculation is simpler to organize.
Enjoy your Friday.
And repeat the parameters until you hit the right.
So should I find a different reaction then?
No, let's do the original for features, but I need to learn more from you about details.
Okay, yeah, I'll make a whole spreadsheet and stuff, and we'll look at it together.
I should start it with you, so you.
That's okay.
I probably talk to Kristen first and then to Steve in a second because your questions are likely to be shorter. You can do Dr. Phyllis immediately.
My main question is, what is the next supposed to be? I think I need the long part. But I don't have the actual map.
Everything except you were reading you were saying
All good? Yep. Okay. Friday after lecture, can we chat briefly? I just want to, if you're willing, you want to learn more where you are.
Okay.
Just briefly, like
Yep.
2-3 minutes.
Okay.
Thank you.
John, if you think that you are impatient or rather you have different things, we can schedule a special meeting. But if you're flexible, I hope to be done in like 5 minutes.
I can wait.
Thank you.
Great.
Thank you for the questions.
So the first thing is the code I have.
I
does-
send you two codes.
Yes.
One that works right away, and another that needs to be run 3 times before it generates something.
Oh, really? So the 92, should that work right away?
If it doesn't,
It does.
I'll take care.
It does not. I tried it a few times, and it did give me the graphs, but it never gave me the spinning video. Which I just ran it, so it's waiting right now.
Oh, okay.
So I'll show you what it pops up with.
So while it doesn't work, let's read things.
Okay.
Mm. It's just complaining for video format. If you do not care about video, one can disable everything related to writing video, and it will work fine.
Oh, really?
Yes.
So I don't need to see the direction. Does this will this tell me the direction it's spinning? Based on just that?
Yes.
Okay.
But making video is the, to some sense, last part. Instead of 1 p node, there are 2 p node,
Okay.
and same for X node. So, but instead of 1 X, there are 2 X and Y, 2-dimensional.
What's the case that there would be one x?
Well, you cannot have. I have very clear so that it just takes me to express verbally. The project that Amelia is doing in the class material today uses one dimension for circular motion because we have angle. Here we are not doing this smart thing. In some sense, it's more basic. So it uses literally position in x, position in y without going to this polar coordinates. So in this version of code, there is no way to use one dimension because it's like plane is two-dimensional. Okay, time is progressing, and something is going on. By changing parameters, if you move, and so you're at least convinced that this version of code runs after giving it a jump start.
Somewhat, yes.
Okay.
Doesn't seem to be moving, but
It's intentionally made to move slower. See, something is changing here. And dispersion, this is not critical right now. So we set up wave packet in X and Y, and then there will be yes. So actual wave packet is product because we have two dimensions and X and Y, we are multiplying it.
okay.
And then this product will have will be matrix instead of vector.
Okay.
I have clear thought. I just making pauses to verbalize. Matrices are difficult to propagate by linear differential equations. Just as the way to record data, it is more comfortable and convenient to convert a matrix into a vector.
Okay.
With the same elements instead of writing book line by line, put it like all big row. Possible.
Yeah.
It's a little silly, but so we set up index like if this I and j run over all elements in this x dimension and y dimension, then we can set up an index as one element plus second multiplied by the size. So this big index will come over, like if this runs over 100, another runs over 100, then big index will run over 10,000.
Okay.
And then we, from this product which has two indices, we set up big psi of big index as a vector of whatever 2,000, 10,000 elements.
Okay.
So this is main idea. The rest will be following this thing. We will go into this super vector and return from this super vector in two dimensions for visualization.
Okay.
Enough? No? You can absorb more? So, as it was set up in our course through the month, in order to propagate wave function forward in time, we need Hamiltonian operator, evolution operator, right? So we need operators. If wave function is one-dimensional, is a matrix, is a vector, then operator is a matrix. But if wave function is a matrix, what will be the operator? an object with 4 indices, which is it is okay, but not very comfortable. But you already have an elegant way of converting matrix with 2 dimensions, with 2 indices, into super matrix, super vector with 1 big index.
So then our new operator would be a matrix for that?
Yes, operators are with the same procedure. We can convert operators from 4 indices to 2 indices of the same nature of big index.
Okay.
Okay. When we were playing with wave function, we had 2 regular indices and 1 superindex. When we deal with matrices, we have 4 regular indices and 2 superindices. So the cycle goes, there are 4 cycles inside of each other. And then we have 2 big indices, right?
So this is the 4-dimensional operator?
Yes. We didn't write it down before. We will define it here. So probably this is the main part. It's already written. It's for another scientific work to learn. But it is the core of the whole code. Do you have something to notes? Okay. you
I have my backpack over there.
Yeah, it will be a couple of lines, but it may help later. Thank you much. So suppose we have Hamiltonian that will act on degree of freedom x, Hamiltonian that acts on degree of freedom y.
Okay.
And they will have I1 J1, I2 J2. We need to combine into super Hamiltonian, that is I1, I2, J1, J2. How do we combine? Can we multiply them?
Probably not.
No.
Maybe.
So I'm not going to offer rigorous proof, but I'll think that I'm confident is correct.
Okay.
So the wave function with depends on J1 by acting of the I1 J1 and putting summation over J1 will be converted into a function I1. Right? So this indices got killed. This
Yep.
one remains and promotes here.
Okay.
But if our wave function is G1 and G2, if our big wave function, what happens to the second factor of wave function if we act with only this part of Hamiltonian? Does it change the second one?
No.
So acting with the first part of Hamiltonian on the combined wave function can be written as Hi1J1 times delta I2J2, which means it will develop no changes for the second factor. Okay? And if we need to act by this part of Hamiltonian, which will affect the second part, it will be the same construction. For the first two indices, it will be delta function I1J1 times Hamiltonian for y, for I2J2. This is our super Hamiltonian.
Got it.
The rest are technical details.
Okay. I don't fully understand, but I get the concept.
Okay. And then right now we went forward from many indices to few indices, and all calculations and propagations with evolution operator are done in this. So this will be big index, like big I. This will be like big G.
This, right?
Yes.
And
Yes.
that would be that one.
Right. And later on there will be propagation. There will be loop in the same way. Loop. Propagation, and after or inside the loop we will be putting like e to the power I as big Hamiltonian delta t h bar on the big wave function, right?
Okay.
To get it from t to t plus delta t. But as soon as we make this time step, this will be with one big index. We need to return to wave functions with two indices just to be able to plot.
Okay.
And there will be a procedure to return back to more.
So you get into this larger Hamiltonian, and then once you get this, you kind of go backwards.
Yes.
Okay.
And then it is plotted, and there are some observables. So those are right now probably there is no time, but one can describe things in the same terms.
Okay.
And, if you just process this idea and then play with code, so I think it is done.
Yes.
And it should generate the movie. If you look, one needs to open it. Yes, there. MP4. Do not worry. I have a suggestion what to do. Let's do it cooperatively. I know part of the game, and you will help with the rest. So let's go to. And if you sign up and try to upload these files, you already have the account for previous assignments, right? So please try to log in and upload these files, and YouTube will just convert it into something more readable. Children's wait. When required. So it's
I think that's why in the code earlier on it said that the if you go up more
no video frames were written to this file. The file may be invalid. Okay, let's see what is going on. 278 213. There's no video writer in here. 213. There's a should we do video writer quotes. Let's check. Maybe it is just a question of the sometimes these tricks help. So it works on Mac, but doesn't work on PC.
Interesting.
There is no rush. We through the Thanksgiving weekend we will get through it. And thank you for being brave. I guarantee you that there will be success.
Okay. And then
But before, while I'm solving, you just process, think about it, and meditate and formulate how to. What can be done, what can be changed, and let's chat and then do a couple of runs.
okay. So what area of the code would I look to find like things I could manipulate?
Oh, just initial values for P, like P naught, X naught.
So here.
P naught, X, yes. Just these few things.
Okay.
And the and magnetic field. Just 5 parameters, nothing else. If you have steam to do more, we can discuss it, but originally it will be more than sufficient.
Okay. Where's magnetic field? This?
Yes.
And then these
4.
These.
P naught X, P naught Y, X naught, Y naught.
Okay. Got it. And this one leave alone, or
Yeah, this doesn't matter.
that's used to help define these.
Yes.
I'm guessing. Okay. Got it.
I would try maybe. They will decline to go into the opposite direction, but you can do counterface like P naught X equals like -10, P naught Y equals +10. It will be this point on the face space, and
That would be opposite symbols.
and then yeah, P naught X equals +10. T0y will be minus 10. Yes. And
Interesting.
and then it will be like. Right now, it is designed to have only one wave packet,
Okay.
but then we can probably duplicate and have two wave packets simultaneously. To practice. Like,
If you manipulate the code somehow.
Yes,
Okay.
but let's.
Not worry
right,
about
right,
that.
yeah, right now I think you have more than enough to practice and to enjoy your curiosity.
Okay.
Good?
Sure. I can deal with that.
Yep. Thank you.
Thank you.